Hello. Welcome back to class. I'm glad you're all on time. So, you know the drill. Say hi in the chat. Let me know who's here. We got a good class lined up today. Probably one of the most important results in the history of society we are going to discuss today. And I'm not even exaggerating. Nobody's saying hi. Oh, there it is. Hey, Jax, good to see you. Good morning, Lauren. Welcome back, Navik. How'd you like linear algebra today, Navik? Good morning, Turner. Jared. James, good morning. Hope you have your coffee ready. It was good. Thanks. All right, we'll get started in, I don't know, 30 seconds or so. Hopefully a few more people trickle in. What's today's shirt? It's an evening scene on the beach. Hello, Molly. Good morning, Jonathan. All right, well, it's 10 o'clock. So if you'd like to participate in the simultaneous sip, give a second for a couple more people to trickle in. Now would be a good time to do so. Good stuff as always. All right, let me see in the chat who joined in with the sip today. James, Navik, Molly, they all sipped. That's great. Turner joined the sip. That's great. All right, so today we're going to talk about some properties of definite integrals. Okay? So I have a list of, I don't know, there's 10 of them here. We'll start with the first 6 and then we'll look at some examples. That's a great point. Don't forget to smash the like button for calculus. Okay, so we'll start with, we'll start our list where most people start their lists with number -1. So this property says that the integral from b to a of f of x dx is equal to negative the integral from a to b of f of x dx. So if you switch the order of the bounds, that comes at the cost of a -1. Okay? Property 0 is that the integral from a to itself a of f of x dx is equal to 0. Property 1, the integral from a to b of a constant is the constant times b minus a. So this is like the first, I mean, I guess property 0 also tells us how to, but this is like the first time we really get to see how to evaluate an integral. Okay, but this is just for the most boring case. When our curve is just a straight line, it's really easy to find the area under the curve there. This would be the height, and this is the width. So it's like length times height, or width times height. All right, property 2, the integral of a to b of f of x plus g of x dx is equal to the integral of a to b of f of x dx plus the integral of a to b of g of x dx. So we can break apart integrals by addition. Similarly, we could factor out a scalar. And then last on our list before we get to an example, it's the same as the addition one. It's combining rules 2 and 3 to give us what happens when we have subtraction. So if we have two functions separated by subtraction, then we could break apart the integrals with a minus sign. Okay, let's look at an example. Okay, so given that the integral from 0 to 1 of x squared dx is 1/3, we actually showed this a few classes ago when we found the area under the curve of 1/3 with a bunch of rectangles. So given that we proved this a few days ago, evaluate the integral from 0 to 1 of 4 plus 3x squared dx. Obviously, we're using, don't use the Riemann sum approximate, or don't use the Riemann sum limit of terms. That's going to be a mess. Use the properties we have here. Okay, so I would start by breaking it apart into two separate integrals. Let me know in the chat. Don't tell me your answer. Let me know the order of the properties that you used when you finally get an answer. All right, so chat's a little bit quiet today. Maybe you guys aren't sure how to get started, and that's fine. Hopefully when I work this out, you'll see it's really not that bad what we're doing. But we want to evaluate this. We could break this apart into two separate integrals using property 2, right? It says the integral of a sum is equal to the sum of the integrals. So instead of having the integral from 0 to 1 of 4 plus 3x squared dx, we could have the integral from 0 to 1 of 4 dx plus the integral from 0 to 1 of 3x squared dx. Okay? The integral of a constant, we could use property 1. So the integral of a constant is the constant times the length of the interval, which is just 4. We don't know what the integral from 0 to 1 of 3x squared dx is, but we do know what the integral from 0 to 1 of x squared dx is, and that's 1/3. So let's factor out the 3 so we could get it into this form, and then we could use that fact. We're allowed to factor out the 3 by property 3. So we just showed that the integral from 0 to 1 of this function, 4 plus 3x squared dx, is equal to 5. Any thoughts or questions about this example? Well, while you type out your questions, I'm going to continue our list. I'm going to continue our list of properties. So number 5 says the integral from a to c of f of x dx plus the integral from c to b of f of x dx is equal to the integral from a to b of f of x dx. Okay, so if you go from a to c and then c to b, that's the same thing as just going from a to b. Okay, so if you make a pit stop along the way, it doesn't affect the entire integral. Six says if f of x is positive, on this interval, then so is the integral. So if f of x is non-negative, then the integral of f of x is also non-negative. Right? If f of x was non-negative, then this integral represents the area under the curve. And so an area obviously is going to be positive or non-negative. Seven says if f of x is greater than or equal to g of x on this interval, then the integral from a to b of f of x dx is greater than or equal to the integral from a to b of g of x dx. And then the last one, which we'll take a look at an example of. if f is bounded below by some number little m and bounded above by some number capital M, I'll get to your question in a second, Jax. If f is bounded below by little m and above by capital M, then the integral from a to b is bounded below. The integral of a to b of f of x dx is bounded below by m times the length of the interval and bounded above by capital M times the length of the interval. Why would we want to split up an integral, you ask? Well, it's possible that our function, and we'll see when we learn how to actually evaluate integrals with more advanced techniques, if our function has some sort of removable discontinuity, our techniques won't apply. So if there's like some sort of removable discontinuity on this interval, it's going to make sense for us to break up our interval at those discontinuities. So typically we would start from this way and move backwards. Also, if we had a piecewise function, right? If our function was defined piecewise and we wanted to do an integral over the entire domain, we'd want to break it up into each of the components from the piecewise function. Don't worry, you'll see examples where it's necessary to break it up. Don't you worry. Okay, let's take a look at number 8. So use property 8 to estimate the integral from 1 to 4 of the square root of x dx. So on the interval 1 to 4, on the interval 1 to 4, the smallest value of the square root of x is, you tell me. And then similarly on the interval 1 to 4, the largest So what's the smallest value on this interval of the square root of x? And what's the largest value of the square root of x on this interval? I know what you're thinking. We have to take the derivative, find the critical numbers, test the function at the critical numbers, and test the endpoints. But think about the graph of the square root of x. It's increasing, right? So we know that its smallest value will be what happens at the left endpoint, and what the largest value is what happens at the right endpoint. What are those values? Yeah, the smallest value of the square root of x on this interval is when we plug in the left endpoint, which is 1. And the largest is the square root of 4, which is 2. So property 8 tells us that 1 times 4 minus 1 is less than the integral from 1 to 4 of the square root of x dx, which is less than or equal to 2 times 4 minus 1. Okay, so we know that this integral is somewhere between 3 and 6. All right. So let's now get to the section that you've all been waiting for. Can I get a drum roll in the chat? Okay, I'm going to pretend that you guys are typing in the drum roll sound. We are going to do section 4.3, the Fundamental Theorem of Calculus. Not a single person typed the drum emoji during that? Come on, guys. We're like stuck in the middle of our houses or apartments for me, but you guys are probably at a house with your parents, bored as can be, and we can't even type a drum emoji for a drum roll for the Fundamental Theorem of Calculus? Bizarre. Truly bizarre. Okay. I'm back. All right. So what is the Fundamental Theorem of Calculus? It establishes a connection. Oh, chat broke. Turner, I don't believe that. Couldn't find any trouble. Okay. What is the Fundamental Theorem of Calculus? It connects what we did at the beginning of the semester with derivatives. It makes a connection with derivatives and finding the area under the curve, which is integrals. Okay, and in fact, there's a very strong connection between the two. Okay, we're going to use the abbreviation FTC. So the FTC establishes a connection between differential calculus and integral calculus. Okay, but before we actually state the fundamental theorem of calculus, we're going to need a little bit of buildup. Okay, so consider the function defined by g of x, so its inputs are x, is equal to the integral from a to x of f of t dt, where f is continuous on the interval a, b, and x varies between a and b. Okay, so what this looks like. So if we have some function f of x, and let's say this is a, and this is b over here. Let's say this is our input for g of x. The value of g of x is the area of this region. I guess I should write the words first before drawing in the lines. Okay, so the area of this region is g of x. So if we let x equal a, it would be 0. There'd be no area under the curve. But if we let x equal b, it'd be the area under the entire curve. Okay, so we're going to let x vary, and it's going to tell us how much area there is so far. So we could think of g as the net area so far function. Okay, so this function is going to play a big role in the fundamental theorem of calculus. Does x represent the endpoints of the function's domain or some arbitrary upper bound? It's just some value in between a and b. So we're going to let x vary between a and b. And at each value of x, it tells us how much area or what's our net area so far. Now, so if a was 1 and b was 10, we could have x be any value between 1 and 10, including 1 and 10. Okay, let's take a look at an example so we could kind of see what's happening here with g. Okay, so we have let g of x be the integral from 0 to x of f of t dt. I haven't drawn f yet. Find g of 0, g of 1, g of 2, g of 3, g of 4, and g of 5. F is the function f is this function. Okay, so I'll give you a minute to think about this. Basically, we want to figure out what is the area between under the curve from 0 to 0. That would give us g of 0. From 0 to 1, from 0 to 2, and so forth. So I'll redraw the function over here because we're going to use it for our answer. Okay, so we want to find the net area so far. Okay, well, starting at 0, right? Why does it start at 0? That's the lower bound of our integral. Okay, so if you start at 0 and end at 0, there's no area. So g of 0 is 0. If you start at 0 and end at 1, our region is this triangle, whose area has length 1 and height 2. So its area is 1. So g of 1 is 1. Okay, g of 2 is the area from 0 to 2. So it's the area of this triangle plus the area of this rectangle. This rectangle has area, well, 1 times 2. So g of 2 is 1 plus 2, which is 3. G of 3 is the area from 0 to 3. This triangle has area 1. This rectangle has area 2. This triangle has area 1 as well. So the total area is 4. Going from 0 to 4, now we have a triangle that's below the x-axis. So we're going to count its area as negative. Its area is 1, but we'll count it as negative 1 because it's below the x-axis. So g of 4 is 1 plus 2 plus 1 minus 1, which is 3. And then similarly here, this has area negative 1. So the area, the net area over this entire region is 1 plus 2 plus 1 minus 1 minus 1 is 2. Is that clear how we got these values? Is there a difference between net area and area? Yeah, so like if I asked for the area of this region, then you would treat these as positive numbers, right? Because what does negative area really mean? So we use the term net area to kind of mean that the stuff below the x-axis counts as negative, and above the x-axis means positive. Right, because what's the actual area of this region? It'd be 1 plus 2 plus 1 plus 1 plus 1, which is whatever that is, 6. So we use net area when we're going to subtract off terms. So let's state the first part of the fundamental theorem of calculus. Which says if f is continuous on AB, then the function g defined by g of x is equal to the integral from a to x of f of t dt. Is continuous. So this is a continuous function. And differentiable function. On the open interval. And here's the amazing part. The derivative of this function the derivative of the integral is the function we started with, is f. Okay, so what does this theorem say? It says the derivative of the integral function is the function we started with. Amazing, isn't it? Jax is the only one that shows any enthusiasm for the fundamental theorem of calculus. Little do you all know, this theorem, and part 2 especially, is going to make our lives so much easier. But that's okay. Maybe Jax is the only one whose chat works. Maybe Turner wasn't actually lying. Okay, let's do an example. I guess let's first just, I have in my notes, roughly speaking, so I'll write it down so you have it. Roughly speaking, if we integrate f first, and then differentiate the result. We get back where we started. All right, let's look at an example. Find the derivative of g of x, which is the integral from 0 to x of the square root of 1 plus t squared dt. I'm going to give you a minute to work on that, and then I'm going to go find my iPad and see if this chat's actually working or not. Oh, come on. So the chat. All right, you guys are just quiet today. That's fine. That's fine. Find the derivative of this function. Well, this is really straightforward, right? Our theorem says the derivative of the integral is just the function. We have it in exactly the form. We have a constant in the bottom. We have x as our top bound. We're in exactly the form we could use, so we could use FTC1. So FTC1 says the derivative of an integral is just the inside function. And we got to make sure we have the right variables. So here we use t as kind of a dummy variable just so we don't have the same variable bouncing around all the time. But yeah, so we have to just switch to the variable that we want to, we're taking the derivative with respect to, and that's it. So the derivative of an integral is the function we started with. All right, well, let's look at another example. This silence in the chat that we have going on today, I'm a little bit used to it because Jax, I'll answer that question in a second. We'll see it with our example. I'm a little bit used to it because this is how my linear class is every day. Nobody chats. Nobody chats. All right, so let's do an example like Jax said. What if the upper bound was not x? So let's say it's a function. Well, let's say if we have a function as our upper bound, well, we're not in the right form, right? Our form to use the theorem is we need a constant, right? Before we could use the theorem, we got to make sure it actually applies. We have a constant, and then we have a variable raised to the first power, no nothing else. What we could do is we'll say, well, let's let u equal x to the fourth. And so we're basically going to just use the chain rule. So we want to take the derivative of our function well, we could switch to the variable u. And then when we take its derivative, oops, sorry. So we want to take the derivative of, here we have a u, but we're taking the derivative with respect to x. We can replace this with the derivative with respect to u times the derivative of u with respect to x. right? You could kind of think of these canceling out. These u's canceling out would be left with the derivative with respect to x still. It's kind of one way to think of it. So by the fundamental theorem of calculus, part 1, this is just secant of u. But we started with x, so we should end with x. Secant of u, well, u is x to the 4th. And du dx, what is the derivative of x to the 4th? That's 4x to the 3rd. Okay, so basically what this is saying is if one of our upper bounds is a function, if the top bound is a function, then you use the same theorem, but you got to multiply by the derivative of the function. It's the chain rule that we're using. Okay, so we could take the derivative, but then multiply by the derivative of the function. Okay, so that's how we deal with it if the upper bound is not just x, if it's just a function. Okay, let's state the fundamental theorem part 2. So fundamental theorem part 2 says if f is continuous on AB, then the way we evaluate the integral from a to b of f of x dx is we evaluate some other function f at one endpoint and subtract the function at the other endpoint. Where capital F is an antiderivative of lower f, of little f. Okay, so what this theorem says, again, this is, will make our life so easy. In order to evaluate an integral, all you have to do is find an antiderivative. All you have to do is find an antiderivative of the function, and then just evaluate at the endpoints and take the difference. So let's look at one quick example. We'll do a ton of this tomorrow. Okay, we want to evaluate the integral from -2 to 1 of x to the 3rd dx. Well, the solution is we need to find an antiderivative of x to the 3rd. Remember how we find an antiderivative of x to a power? We increase the power by 1 and we divide by the new power. So f of x is equal to x to the 4th over 4. So the integral from -2 to 1 of x to the third dx is equal to x to the fourth over 4 evaluated at -2. And I'll use that notation tomorrow. -2 to the fourth over 4 minus 1 to the fourth over 4, which is equal to -15 fourths. Okay, so this question, which would have taken us 20 minutes with our Riemann sum formula, took us 5 seconds. Okay, I know we kind of rushed through this last example, but we'll spend so much time doing it tomorrow. You'll get sick of it. All right, well, it's time. Class is 10:50, but so I'm out of here. I have office hours at 11. I don't know if I'm just talking to Jax right now, or if you guys could all hear me. But yeah, we have a quiz tomorrow where I sent you the email with what to expect for it. Either approximating some sort of area, or writing an integral as a limit, or actually evaluating an integral using limits. But yeah, I'll stay around here for a minute or so to answer any questions. But remember, hit the like button before you get out of here. It's very important. But yeah, I'll see you tomorrow. Turner, you said the chat's broken. Now you're saying bye-bye. Okay, you want to either ask me now, Jonathan, or you want to come to office hours in 9 minutes, if it's easier to ask over Zoom. All right, Turner, I'll see you tomorrow. Thanks, Navik. When you're solving R sums, when you're solving R sums, how does going from the left or right affect the equation? Yeah, so it just depends on if, for approximations, I'm assuming you're talking about. It's gonna change what the sample points look like. So if Riemann sums, yeah. Yeah, so if like we had, this was our interval, and let's say n equals 2. If we were using left endpoints, this would be a sample point, and this, so let's say it's 0, 1, and 2. If we use left endpoints, then we'd evaluate the function at 0 and 1. If we use right endpoints, we do 1 and 2. Delta x would be the same. Yeah, the only difference would be x sub I would be different. Yeah, for left endpoints, it'd be a plus I minus 1 delta x. So slight difference there. But if you had a fixed number, you just have to read them out. If we're doing the limit as n goes to infinity, it's exactly the same. All right. I'm out of here. See you at office hours if anybody wants to come. Bye-bye.